leaders such as Cadence Design Systems, Synopsys India, and Magma Design Automation. He has been involved in developing some of the well-established industry standard EDA tool for clock synchronization, constant management, STA, forward verification, and physical design. He has been teaching semiconductor specific courses since 2016 at IIT Delhi. His teaching has been rated excellent by students consistently, and he has received the Teaching Excellence Award for 7 consecutive semesters at IIT Delhi. His current research interests are in the area of VLSI design and automation, energy efficient systems, computational networks. He is the author of the book Introduction of to VLSI Design Flow and Fundamental of Industrial Transistor and holds 3 US patents. He is an editor of IT Technical Review and associate editor IEEE Access, a reviewer editor Frontiers in Electronics Integrated Circuit and VLSI and senior members of and senior member of IEEE. Now I request to Professor Ismi Swarab to please enlighten us with their thoughts. Okay, sir. And over to you.
Thank you, Professor Gaurav. So, hello everyone. Can you hear me? Can you hear me? Can
Yes,
anyone
sir.
confirm?
Yeah, we can hear you, sir.
Okay. So, uh, let us start with the presentation. So, let me start my presentation. Can you see the presentation?
Yes, sir. Yes, sir.
Okay. So, let me start. Okay. So, in this talk, I'll be basically describing or giving an overview of VLSI design flow, right? So, it will be an overview, and I'll be looking more at the fundamental stuff. And if you have questions, I will at appropriate times I will pause and ask you allow you to ask questions. So please feel free to ask questions. So and make this session interactive and lively for all of us, right? So in this presentation or in this talk, I'll be covering the following topics. First, I'll be looking into some basic concepts related to integrated circuits. Then I'll be going into a top level view of what a VLSI design flow is. And then I'll be briefly discussing what is pre-RTL design flow. And then I'll be looking into logic synthesis. And then I'll be going into integrated circuits. So this is the outline of my talk, and I hope I'll be able to cover all of them in 1.5 hours, right? So let me start with some basic concepts related to integrated circuits. Okay, so first let us look into what is an integrated circuits and how does it look like, right? So if we take any integrated circuit or any chip and take a vertical cross section means that we cut it in a vertical way, then we will see the structure something. So this is a vertical cross section of an integrated circuit. So in this integrated circuit, we can identify two different types of layer, right? Right. So at the bottom, we have what are device layers, right? So at the bottom, we have device layers where we have the MOSFETs, transistors, FinFETs, and those kind of things. So the device layers are the layers where we have the devices like transistors, capacitors, and so on, which we want in our integrated circuit. So in an integrated circuit, in typical integrated circuit these days, we have more than millions of transistors, right? So in this figure, we can identify that these two are the transistors, right? Now, below the device layer, sorry, above the device layers, we have multiple layers of interconnects, right? So interconnects are basically the copper wires which connect one device to the others, right? So you have transistors which are connected with each other. They can be connected using polysilicon, or they can also be connected using wires like coppers, right? So these are the upper layers have many layers of coppers which are separated by dielectric. Dielectric means silicon dioxide, which is an insulator, right? So we have copper and another layer of copper, one running uh, but this direction, other orthogonal direction. The next one running in the original vertical direction, and the next one in the orthogonal direction, right? So we have different layers of coppers, and they are separated by dielectric, and one layer of copper with the other and the other layer of copper is connected using what are known as vias, right? So one layer of copper is connected with using to the next layer below it or above it using vias, or vias are also interconnects of a kind of metal which connect one layer to the other, right? So this is how the integrated circuit looks like, right? So now why we want to go why do we want to understand this structure? So we want to understand this structure during designing, because see, the goal or the what the main focus of this lecture or is to discuss how we design our chip or integrated circuit. But to design it, we should at least have some fundamental of what an integrated circuit looks like. Why? Because during design step, must understand, or we are actually finding these patterns of these interconnects and the device layers, which must be put in our layout, right? The final goal of a design is of a design step is a layout, right? But in layout, we describe various patterns, and those patterns are basically fabricated in an integrated circuit. So our goal during designing is to find a layout. Layout we finally fabricated in an integrated circuit. And what steps do we use to fabricate? How do we fabricate these various layers? We fabricate these various layers using a process which is known as photolithography, right? So, what is photolithography? Photolithography is a fabrication task in which we pass light through a mask, right? So the mask is a glass plate over which there are patterns, right? There are patterns of the layout that we want on our chip or on our die, right? So the mask is basically prepared using the design that or the layout that we will make, and using this mask, using some chemicals and other process steps, we get a replica of that mask or that design on the die, right? And this die is but integrated circuit, right? So the goal of the design is to make a layout which will finally be turned into a mask and then fabricated into into an integrated circuit using a set of processes, and the key step is the photolithography, right? So any questions till now? Am I audible?
Yes, sir, yes, sir.
Okay. So if there is any question, please ask. There are online audience also, and there are offline also. You can ask questions. Okay. So let me continue. So now, when we fabricate our integrated circuit, then we fabricate it on what are known as silicon wafers. This is a figure of silicon wafers, right? So these silicon wafers are typically of the sizes of say 300 millimeter diameter. So this is the size of the chip, right? So this silicon wafer is size of a plate or thali that we use, right? For that is what size of these wafers are, right? Now on this wafer we fabricate multiple dies. So one this black rectangle is what we call is a die, right? So this is die. So the expanded view of die is this, right? Now on this die we will have actually millions of transistors. This is a complete design. On this complete design will be fabricated on a die, right? So this die is then once we have this die is fabricated using our layout, which contains millions of transistors, right? So the transistors will be sitting on these dies, and this die, this die, the size of these dies are a few millimeter square or centimeter square. Right? That is the size of these dies. So on these small pieces of silicon, we have millions of transistors, and these are fabricated using our design or our layout. And once those are fabricated, those are packaged using some packaging material, and then this die, when they are packaged, we get the chip, right? The chip has all, so you have seen the chips, various pins, so on, and those will be finally integrated into the boards, and we get the electronic products and so on. So the design step will be basically going into these dies, right? So designing what will be the layout, those layout will be basically converted or fabricated on the dies. Those dies will be placed into a chip, and then chips are used in our electronic products. So in today's lecture, we'll be discussing that how to design this chip or how to make the layout of a chip, right? So when we make a layout of a chip, right? So the one of the important thing that we consider is the figures of merit, right? So what? So when we want to design a circuit, when we want to design a circuit, then we are given a functionality, which means that this chip needs to be working as a processor or a microcontroller or some some other Bluetooth chip or Ethernet chip or something, right? So the functionality of a chip is defined, right? Now that functionality can be implemented in many ways, but figures of merit will differ, right? And what are these figures of merit? The figures of merits are such that power. One of the figures of merit is power, meaning that how much power does our chip consume. So this power can be either static power or it can be dynamic power, right? So the static power and dynamic power are the total power that is consumed by the chip, and we must be considering it as a figure of merit. The next figure of merit is the performance. Excuse me. The second figure of merit is performance. So performance is measured using the parameter like maximum operable frequency, right? So, and the third parameter is the area. Area of the chip, we should want that it should be as small as possible. Why we want this uh, area of our chip to be small? Because if the area is small, we will have four chips on the same wrapper, right? Therefore, will be the cost of the chip will come down. So we want that area should be coming down. The performance or the maximum operable frequency go up, and the power dissipation should come down. Ideally, these things we want in our chip, right? And once we have designed our chip, we can report numbers, power, performance, area combined are known as PPA. P for power, P for performance, and A for area. Right. So we combine three parameters or figures of merit are known as PPA, and we quote that our chip has a power dissipation of 1 watt. It maximum operatable frequency is 1 megahertz, and area is 1 millimeter square. This is just an example, right? Now, an important thing to remember is that uh, whenever we design, see, this cannot attain all these PPA goals at the same time. Meaning that whenever we increase the maximum operatable frequency, then what happens is that typically the area goes up, right? So one figure of merit improve, the other can actually come down. So the performance can go become better, but the power and area can is a bad thing, right? On the other hand, if you try to reduce the area, what happens that we may be having that the performance of a chip may come down, maximum operatable frequency may come down, right? So this, therefore, designing is always a kind of a balancing act where we want to find a good balance which satisfies our requirement. We cannot optimize all of the PPA measures at the same time, right? So we when we want to say improve our maximum operable frequency, then the area will be traded off. That the area will increase and we have to live with it, right? So designing always is finding a good balance between the figures of, right? Any questions till now?
No question, please complete this.
Okay, so let me move forward, right? So, okay, so the now let us look into the top level view of VLSI design flow. What is the VLSI design flow? So I think that someone has put their mic turned on the mic. So can you please put off because lot of noise is coming out. Uh, is any participant in the online mode has turned the mic on? Okay, so I think, yeah. So uh, let me continue. Uh, a lot of background noise is coming. Can you please check that whether uh, the the mic at the end where you are having offline lecture is turned on? If it is turned off, please mute it because it's creating echo also.
The Gaurav sir's mic is creating echo.
Uh, can you please turn off the mic? Yes, now it is much better. Okay, thank you very much. Okay, let me continue. If you have questions, then please turn on your mic and please ask. Right. Okay. So now let me give a top level view of VLSI design flow. So now what is VLSI design flow? So VLSI design flow is basically a technique of realizing a chip, right? So we have got some initial idea that we want to make a chip which fulfills some desired functionality, right? That functionality can be related to processing, that can be related to some controlling, or that can be related to some communication kind of chip or so on. So we start with some functionality or what we want to do, what we want to achieve with our chip, right? And the final goal is that we should have a chip which delivers that required functionality Of course, it should also satisfy our constraint in terms of speed, power, and other things, right? So this is the what goes in this, what various tasks are carried out in this journey from idea to chip. That is what is known as VLSI design flow, right? So now this is a very complicated problem from going from the idea up to the chip, right? But and therefore this complicated task we want to solve using what is known as divide and conquer technique, right? So we don't attack this problem in a one step. What we say is that let's divide this big problem into small steps, and then carry out each step in a kind of flow, or in a set of processes which is arranged in a type of a flow, and we get what is known as VLSI design flow, right? So now this task of designing a chip is basically has got a few important milestones, right? So what are these milestones? So the first milestone is the RTL. So from the functional description, so we have functional description of our chip. From the functional description, we derive or we get an RTL, right? So what is an RTL? RTL is the description of the functionality in hardware description languages such as Verilog or VHDL. So RTL stands for register transfer level, right? So given a functionality, we obtain an RTL, right? And then we convert this RTL to the layout, and this layout is represented using a database which is known as graphical database system, or GDS, right? So these are two very important milestone in the design flow. One is the RTL, the final is the GDS or the layout, right? So the before this RTL, before this obtaining this RTL, what we have is known as the idea to RTL flow or system level design, right? So the idea to RTL flow is those set of design tasks which takes a high level description or the concept of product, right? This is at this level, and represents the hardware portion of the implementation in the RTL. So from the idea, we get the RTL, right? And this is the RDR to RTL flow or the system level design, right? And the next part is from the RTL to the GDS, right? So RTL is basically description of the functionality in hardware description language like Verilog and VHDL. And from this Verilog or VHDL design, we get the layout, and that is what RTL to GDS flow is, right? So the RTL to GDS flow is from this part to this part, right? So RTL to GDS flow takes an RTL through various stages of logical and physical design steps, and finally we get a layout represented in GDS. And once we get a GDS or the layout, this is sent to the foundry, and then the fabrication is done, right? And this is GDS to chip flow, and from in that GDS or the layout is converted to chip using fabrication processes, and in this case this is a mass production, right? So from there, from the layout, we get chipped in a mass production way, right? For example, if we have designed a processor, right? We have designed a processor, we have made the layout of the processor, then that layout will go to the foundry, and say 1 million processors will be fabricated, right? So that is the fabrication step. So the designing step is from idea to layout. This is the design step, and the rest step is the fabrication. So we'll be discussing in today's lecture this part from the idea to the layout. Okay. So the designing part is from idea to RTL, RTL to GDS. This is designing part, and the GDS to chip flow is the fabrication or manufacturing. Right. Now let us look into the pre-RTL methodology, right? From the idea to RTL, what things happen, right? So this is also known as system level design, right? So let us briefly discuss system level design. What is system level design? So in the system level design, what the initial step is that we first evaluate the idea, right? We have idea that we want to make a microprocessor, for example. Then we must first understand that whether there is a requirement of that idea, we need to do some market research and understand the requirement, and whether the idea is feasible or not. Feasibility not only in terms of technical, but also financial, meaning that whether it will be leading to profitability or not, right? At the end of all this manufacturing and making a chip, our goal is to make profit, right? That is the whole idea. And therefore, the first thing is that we should first evaluate whether an idea is feasible and it will lead to profitability and so on. And we refine the idea based on these inputs, right? So the evaluation and refinement of idea is, once we have refined the idea, we create a specification for the product, right? So we create a specification in which we say that we need these kind of functionality, right? For example, we need this kind of instruction set for a processor, or these features should be there in a communication chip, and so on. For example, whether there should be a security feature or not, which kind of security feature should be there. So those details are first worked out, and we make a specification for our product or whatever the chip we are designing. Then we also prepare our PPA goals, right? What should be maximum operating frequency that our chip should have, right? What should be the maximum power dissipation we can tolerate, right? What should be the area of the chip, maximum area of the chip that we can have, right? So these things will actually determine our profitability, yield, and many other things, right? And therefore, this preparing the specification is very important. Another very important thing is time to market, right? So in our semiconductor industry, the one of the biggest thing is the competition, right? So we always want to bring our product or launch our product as early as possible, at least before our competitor, right? And therefore, those kind of things sets constraints on our schedule, our design schedule, that by this much time, within 9 months, within 12 months, or whatever the time schedule is, we must be ready with our layout or our design. So that will be coming from the market requirement, and this is a time to market is one of the important specifications that is initially specified and which must be met to obtain the desired goal of profitability and other things, right? So so this specification is prepared, right? And once the specification is prepared in terms of functionality, PP and TTM, what we do is hardware software partition, right? Now once we have our specification, we will think that which portion of our specification can be satisfied by software running on a general processor, right? For if we are, for example, designing an SoC, right? In this SoC, there can be a built-in microprocessor, and there can be other components, hardware components, accelerators, and other things. So we can have a microprocessor in our SoC or our big design, and on this microprocessor our software can run, right? So many of our functionality can actually run on this general purpose microprocessor, either within our chip, or in this microprocessor can be also outside our chip, which will be integrated later on. So the specification is partitioned into hardware portion and the software. The software portion runs on a general purpose microprocessor, and that software goes through software development cycle, right? And the hardware portion, for example, if we are saying that we'll be having this kind of memory, this kind of accelerator, these things we must be having in our chip which we are designing, then we need to prepare a specification, individual specification for each part that we will be making in our hardware, right? For example, whether we will be having a security chip or not, whether we'll having a power controller or not, So these kind of things will be decided at this level, and we will prepare individual specification for those hardware components. And then that using that specification, it will go through the VLSI design flow, and we will finally get the fabricated chip. And once these fabricated chips are received from the foundry, these will be combined with the general purpose microprocessor and the software, and finally we get a system, right? And this system will be the final product, and this will be finally going to the market. So the important thing to note here is that you should have a top level view of the system. So at the system level, you don't have only the hardware, right? So as a hardware designer, we focus a lot on VLSI design on hardware, but that hardware always gets integrated with the software, and in the product we have both the hardware and software which delivers the required functionality, right? So this big picture you should always have, that the hardware is integrated with the software, and the hardware part and the final system needs both of them to work together, right? So any questions till now? Okay. So yes, is there any question? Okay, I think there is no question. So let me continue forward. Okay. Now let us move into the RTL to GDS flow. Let us assume that given our system hardware software partitioning and the specification prepared for the hardware, we have got an RTL, right? So this RTL can be obtained either using, say, high level synthesis, or it can be obtained by manual coding, right? Manual coding of RTL, meaning that we write the Verilog and VHDL code for the given specification. So first one could be hard high level synthesis, the second one could be manual coding, and third would be maybe we have this IP already, right? For example, we have got some functionality of, say, of power controller, and we had already designed power controller earlier, or some other vendor is already giving this RTL for this power controller, then we can have that IP simply and put it in our design. So we assume that we have got the RTL or the design in Verilog or VSTL, and then from there onward we move to RTL to GDS. So now let us understand what happens in the RTL to GDS flow. So in the RTL to GDS flow, right? In the RTL to GDS flow, typically we divide it into two parts. The first part is logic synthesis, and the second part is physical design. So RTL to GDS flow is divided into the two parts. The logic synthesis basically designs, takes the RTL and it converts into a netlist. What is a netlist? We'll see. And the second part is the physical design. So in the physical design, what we do is that we take the netlist and do a layout for it, right? So we create a layout for our chip, right? So from the netlist we get the layout, right? So in this flow, in RTL to GDS flow, we should understand there is an important concept of abstraction, right? So what is abstraction? Abstraction means the hiding away the detail. So whenever you have abstraction, it means that there is less detail in your design. And as so in when we do designing, in the initial stages of our design we have higher abstraction, right? Meaning that we have less detail in of our design. So what we mean by detail is the information, right? So at the RTL level, if we think of RTL level, at the RTL level we have Verilog code or VHDL code. So in this, the Verilog code, we do not have the information of the transistor. We do not have the information about how the transistors are connected, how the cells are placed on the layout, how the what kind of cells are there, right? We only have the functionality at the top level, right? At the RTL. As the design progresses, those details are added. For example, in the netlist, we have the information that which logic gates are used in our circuit, right? And from netlist, when we go to physical design, then we have the where the transistors are there on the layout, how they are connected, how they are placed. Those information is there in the layout, right? So as we go from RTL to GDS or from RTL to layout, details go on increasing and the abstraction go on decreasing. At the top level, we have large level, the high level of in abstraction, meaning that there is less information in our design. So why the design flow is designed in this way, or why we follow this way of abstraction? The reason is that when we are at the top level design, we have less detail and therefore we have more freedom, right? Freedom meaning that we can make many changes in our design in the RTA. As the design matures, it goes to netlist and to layout, making changes into the design becomes more and more difficult, right? And therefore, in the early stages of the design, for example, in the RTL, where making changes are easy, we do a lot of exploration and find out various alternatives and choose the best alternative. So as a designer, we have the greatest freedom at the RTA level, right? At the RTA level, we have greatest freedom or great flexibility, right? We have great flexibility at the RTL level, right? As we go down and down the design flow, this flexibility goes on decreasing and decreasing. And finally, when we get at the layout, there is no flexibility, there is no change, that making change to the layout is much more difficult, right? And that's why we have this kind of RTL to GDS. Okay. Any questions till now? Okay, so let me move forward. Now we'll go into the logic synthesis step, right? So we saw that RTL to GDS step consists of logic synthesis and physical design. So let us go to logic synthesis. So what is logic synthesis? Converted to an equivalent circuit as interconnection of logic, right? So in and logic synthesis, what inputs do we give? The inputs are the design in RTL, design or RTL, which is written in Verilog or VSDL or a mix of Verilog and VSDL. And then we give library, right? So library is a collection of cells that will be used in our design, right? So we have these libraries, these libraries comes from foundries, or using the foundry models, these libraries are designed, and the information of each cell meaning that there can be a NAND gate, NOR gate, AOI, and various kinds of logic gates. Those are designed at the transistor level, and the information of those cells are put in a file which are known as library files, right? So the format of this library file is Liberty. This Liberty is from Synopsys, right? So in the Synopsys, in this Liberty format, we have library, and typically the extension of these libraries are .lib, right? So you might have seen that if you do design flows, then you have .lib file which are necessary for doing your logic synthesis. So you give that Verilog file, the .lib file, and the third requirement is the constraint file, right? So constraint is written in a format which is known as SDC. So SDC stands for Synopsys Design Constraints. right? So we have this synopsis design constraints file of HDC file in which the constraints of the design of our design are specified. So constraints means that at what clock frequency we want our circuit to operate, right? What is the nature of the signal which is coming inside our circuit? What is the nature of the signal which we want to produce, right? So these are the constraints which our design must fulfill. So these design goals or constraints are specified in the HDC file, and these three are the major inputs. Some inputs which are required by the tools which can be given to the logic synthesis tool, and at the end of logic synthesis, what the tool will produce? It will produce a netlist. Now, what is a netlist? Netlist is basically the interconnection of logic gates, right? So, netlist is an interconnection of logic gates. It can be represented either in a Verilog format, or it can be shown as a schematic to by the tool, right? For example, let us take an example. Before looking into the example, let us let us see a few example of the tools, right? So, which tools does logic synthesis? So, in industry, the most widely used tool for logic synthesis is design compiler, which is from Synopsys, and there is another tool from Cadence, which is Genus, which is right. And there are some open source tools also which can be used for logic synthesis. One of them or widely used is YoSys, right? So this is a tool which is open access. You can download it from internet and use in your designs. This YoSys tool, right? And this is for logic synthesis, right? Now let us look into an example of that of logic synthesis. What is actually done in a logic synthesis? So suppose this is our RTL code, right? This is an RTL code which is written in a Verilog format, right? So this is a very simple Verilog code. If you don't understand Verilog, it's okay. I'll just describe what it means, right? So in this code, there are two basic constructs. One is this and this. So first, the inputs and output of our design are defined here, right? In this statement, so inputs are A, B, clock, and select, and outputs is the out, right? And this statement assign y is equal to, if select is equal to 1, then the value of y will be b, else the value of y will be a, right? So this is an example of how a multiplexer works, right? So you, if you know multiplexer, the multiplexer, you have an input, right, which is known as a select input. If select is 1, right, then some input is selected. If select is 0, then some other input is selected at the out, or that is produced at the out, right? So this is how the multiplexer works. So this is a description of a multiplexer in a Verilog language, right? Now the during logic synthesis, the tool will understand this input, this assign y is equal to select, then b else a, and based on its understanding that this translates to a hardware element which is known as multiplexer, the tool will put a multiplexer in our design. The logic synthesis tool will put a multiplexer in our design. The next constraint is always at the rate of causes clock, out is equal to y, right? So this is a description which is similar to a flip-flop. So in a flip-flop, whenever a clock signal comes, then whatever is at the input, that is produced at the output. Otherwise, whatever was at the output, that remains as the same value. It holds the previous value, right? So this is a description of a flip-flop, and the tool will understand this description, and in the netlist, it will put an instance of a flip-flop, right? So how will our netlist look like after logic synthesis? It will look like something like this. We will have one multiplexer, right? Because of this line of code, and the other flip flop because of this line of. So the tool can show this schematic, or if we tell the tool that write a netlist for us, it will write a netlist and it will be in an ASCII file which we can open using any editor, and it will have something like this. So here we have two instances instances, one of a multiplexer and another of a flip-flop, right? And they are connected A, B, and select Y, and this is the D input, the clock input, and the output is connected to the output of our design, right? So the tool will produce this netlist either in as a file which we can view in an editor, or it can show us an schematic which we can view using a schematic a viewer of the tool, right? So this is the what is that now a question will come that which flip flop will be put in this, right? Which flip flop will be put, or the see there can be many different types of implementation of flip flop. Which implementation of flip flop will the tool put in our design? So the which kind of flip flop, which kind of multiplexer will be put in our design, that will be defined by the other inputs that we have went to the logic synthesis tool. Remember that the other inputs that we gave was .lib file, the library file, and .hdc file or the constraints file, right? So using these two information, the tool will pick the right set of flip flop or the instances or the multiplexer and put it in our design, right? So suppose our library contained a multiplexer cell mux2 and a flip flop DFF, then the tool will actually pick this multiplexer and put it in the netlist. It will put this DFF from the library. So this is a library which we have given as input to the synthesis tool. That is the .lib file that we have given to the tool. The tool will pick right right cells or logic gates from our library and put it in our design or our netlist, right? Now, if in our design in our library there are multiplexer of different sizes and other things, then which of these multiplexer will be picked? That will be defined by the constraints, meaning that if we set a constraint where we are saying that we want to have a design which should run at very high frequency, right? If that is the situation, then in that case the tool will pick the cell which is of larger size. Why it will pick the cell of larger size? Because typically the cell of larger size will have bigger transistors, and therefore it can drive fastly the load, and therefore the speed will be higher, right? So depending on what constraints we have used, whether we want our chip to work at high frequency, low frequency, and so on, the tool will pick the right set of cells from the library. The right cells, meaning that of right functionality and right sizes, right? See, the tool will not pick always pick it. The tool will not always pick cells of the maximum size. Why? The reason is that the goal is not always to increase the clock frequency, right? The goal can be also to reduce the size of our tip, right? So if the tool will pick always the cells of larger size, then the size of our design will increase, right? And that is not a good thing. So the tool will pick the optimum size of the cell which will meet the frequency requirement and will not incur extra area cost. So those things, which cells to pick and from which type of cells or what functionality of the cells to be picked, those are governed from the library files and the constraints. Okay. Any questions? Am I audible? Can anyone please confirm if I'm audible?
No, simply certainly.
Okay, okay. Thank you. So now we go to the next part, that is the physical design, right? So once we have got the netlist, then we carry out physical design. Now in physical design, what various design tasks do we carry out? So and what is physical design? So the physical design is the process by which a design in a form of a netlist is converted to an equivalent design in the form of a layout or GDS. So we have a netlist and we want to get a layout, right? So this is the basic goal of physical design, to get the layout. So in the creating the layout, there are two major tasks, right? Two major tasks. One is to place each entity on the layout at right position, right? So for example, you have millions of logic gates in your circuit, right? So where to put each logic gate on the layout, that is a major decision that the tool needs to make. And the other major decision is how to connect, right? So you have two cells, you can connect in one particular way, you can take another route and connect in the another, right? So the in the physical design process, these are two major decisions that the tool needs to make: how to, where to place these cells, and how to connect these. Okay. So what inputs do we give to the physical design tools? So the inputs that we give to the physical design tool are the netlist, right? So netlist, from where did we get the netlist? So netlist was generated by the logic synthesis, right? So when we did logic synthesis, at the end we got the netlist. That netlist is given as input to the physical design tool, right? And then we have the library, right? So we need to give the same library which we use in the logic synthesis, right? So logic synthesis, we gave an input to the we gave various libraries as input to the logic synthesis tool. Those libraries must be given to the physical design tools also. Why? We need to give those libraries as inputs. So the one of the major reason is that the netlist contains objects which are, or which are defined in the library. Now, if we give netlist and we do not give the library, then the physical design tool will not be able to understand what is the meaning of which cells are this, what are the attributes of this cells, and other things. So the cells will be not be recognized, or their attributes will not be understood if we don't give the same library which we use during netlist. Now, in addition to the .lib file, uh, or the library files that we give during logic synthesis, we also need to give what are known as library related to physical design or physical information of cells, right? So why this is needed? This is needed because the cells are say a rectangular object, right? For example, this may be the inverter. Now on this inverter, we have that this is the input and this is the output. And during physical design, the tool needs to connect the input and the output and do the route, right? So the tool needs to know the structural information about the cells also, right? Meaning that what is the bounding box of the cell, where the cells in the cell, the pins are located, and so on. So those information are given in a set of libraries which are known as LEF file, which is LEF, right? So LEF stands for Library Exchange Format. Library exchange format. So these left files are basically used in the cadence. Similarly, for synopsis tools, there are other way in which we need to give the information about the bounding box of the cells and so on, right? So we need to give this information of the some physical attributes of the cells which were used in the netlist during physical design. Yeah, additionally, we also need to give the constraints here, meaning that what is our design goals related to frequency of the clock, what is the expected time?
Well, sorry, just an interruption. We got one question, so just
Sorry?
we got one question. Snehal, Snehal, can you ask some question? You have raised your hand. I don't know. Okay, please continue.
Okay. So if there are any questions, please feel free to interrupt, and I will stop, right? And then answer your question. So, in addition to the libraries, we also give the constraints where we have the design goals like what frequency we must be met by this layout, right? And the environment, right? What is the slew of the coming incoming signal? Whether there are any delays in the incoming signal? What slew we want our design, physical design to sorry our layout or to be producing, right? So these kind of constraints are there, and this is also specified in SDC format, right? Similar to logic synthesis. And we also specify the floor plan, right? Meaning that what would be the bounding box of our design, right? So if we are if we are making a layout of the design, the tool will create a layout for us, but at least we must say that the size of our layout should be this many, this by this size, right? So at least the bounding box or rectangle within which our layout should be made, those things must be decided by a designer and given as input to the physical design tool, right? Additionally, we might want to say that these are the input ports we want to place in this particular way on the periphery of our layout. These are the output ports, and these must be played out put at these positions in our layout, and so these are known as IO cells. So we may want to specify the location of the IO cells, power cells, and so on. So these are the inputs which must be given by a designer to the physical design tool, right? And once these inputs are given to this physical design tool, the tool will create the layout for us, and this layout will be sent to the foundry for fabrication, right? Now, what are so these are the now which tools are there, commercial tools which we use, which we use for carrying out physical design tasks. So the most widely used tool is Innovus from Cadence, and we also use ICC compiler or IC compiler from Synopsys. So these two tools are open source like OpenRoad or OpenLane, which which can be used for physical design too. So these tools can be downloaded from freely from internet, and physical design can be carried out using this. Any questions till now? Okay, so let me continue. So now we go into the depth of physical design, meaning that we got the netlist and finally we want to get a layout. What are intermediate tasks which are carried out during physical design? So the intermediate tasks are placement.
Sir, sir, there is one question.
Yes, please ask.
Sir, in GDS output file, all the schematic which was in the logic gate form that will be converted into transistor level design. That means that in GDS file, all the circuit will be of transistor level only. It will not contain logic gates. Sir.
Right. So the final GDS that we have is the layout, and at the layout level, we don't have even transistors. What we have is only rectangles and trapeziums, right? So this GDS contains the layout information in the form of rectangles that will be used during photolithography for fabrication, right? So when we have this netlist, At the netlist level, we had, say, gate, for example, we can have an AND gate, OR gate, NOR gate, AOI, flip-flop, and so on. Right? At this netlist level, we have that description. But at the end, this AND gate, we said that this information, that what is an AND gate or NAND gate at the transistor level, that those information are continuous before doing the undertaking the designing at VLSI design flow level. The designing is done at the transistor level for all these is known as the library characterization, right? So there will be designer whose task would be to make gate with the transistors and create a layout for it in an optimal way. Once that AND gate is made, then the information of that AND gate extracted from the layout and put it in the .lib file, .left file, and other formats, which has some abstract information of these cells and which will be subsequently in the design flow. Once we have done all this, we have created the layout, then the transistor level description of this AND gate, OR gate, and those things will be plugged in into our layout, and at the end we'll be having a layout in which we have only transistors. And from the transistors layout, we'll be getting from the transistor layout, we'll be getting the patterns of rectangles and trapezium, which will be representing the transistors, and those the layout in terms of rectangles and trapezium will be sent to the foundry for fabrication, and that is basically the GES. Okay. Hope I have answered your question. Is there any further question?
No, sir. This was the
So let me continue. So now we'll be going into each design task within the physical design process, right? So the major tasks are chip planning, placement, clock tree synthesis, global routing, detailed routing, and each flow. So we'll cover these tasks in some detail now. Right. So the first task in physical design is chip planning. So in chip planning, what do we do? In the at the chip planning level, we basically take certain major decisions related to physical design. What are these major decisions? The first is that we might partitioning our design, right? So we might be partitioning into various blocks. For example, if we have a big SoC, in that SoC there can be various processors, there can be multiple cores, there can be multiple memories, there can be multiple controllers, and so on. So we might be partitioning into various blocks, and each block might go through various physical design process, and at the end, the physical at the end, those blocks will be integrated together and we get the layout for the SoC, right? So that may be the first step would be the partitioning. Can you please mute at your Okay, thank you very much. Okay, so the first part is partitioning. So you be partition our design into various blocks, and each block may be going through physical design tasks separately, and then at the end we combine together at the top level, right? So that may be the first task to be partitioning. Then the other thing is that we might be want to place the bigger entities or blocks over the die, right? So this is our die, and we want to say that we want to put a memory block here, the CPU here, controller here, another portion of the big block here, and some portion is left for standard cells and so on. So the bigger portion, big parts of our design, those are placed over the layout, typically manually, right? So at the chip planning stage, many of the tasks are done manually, right? So though we take help of the tools, but many a times human intelligence works better in at the top level when there are fewer entities in the design, and we have past experience of making better layout and other things, right? So during chip planning stage, a lot of manual interventions are done to arrange the blocks on over the die, right? So these are bigger entities, big blocks, maybe a memory controller, maybe core, multiple cores are there. So those big blocks are placed over the die. Then we allocate area for the big blocks and allocate area for the IO cells, right? So we allocate area of the IO cells, meaning the cells through which the signals will enter our chip and leave our chip. Excuse me. Okay, so we need to place the IO cells during the chip planning stage. We need to place the bigger entities, which are known as macros, over the layout during the chip planning stage. We allocate area for the standard cells in our design. So the standard cells that we have, or the cells that we have in our libraries, typically, we design them such that the height of the standard cells are fixed, right? So if the heights of the standard cells are fixed, then width can vary, but the height is fixed. So we can arrange the standard cells in the form of rows, right, of the constant height, right? So this is one row of standard cell. This is another row of standard cell. This is the third row of standard cells. So the height of the standard cells are fixed for in the library. Typically, we follow this convention, and because of this convention, we can place standard cells over the in the form of a row, right, of a fixed height, right? So during the chip planning stage, we say that where in which portion of our design this standard cell will be there, what will be the location of these rows of standard cells, and so on. Remember that we are only saying that where these standard cells rows are there. We are not placing each standard cell in the rows exactly at the location during chip planning. Why we are not doing it? We are not doing it because the numbers of standard cells in our designs will be huge. It will be in millions. And therefore, we cannot manually place those standard cells over the layout during the chip planning stage. During chip planning stage, we only place bigger entities like say memory block or the CPU or the controller, big block of things are placed at the required location manually during the chip planning stage. But a huge number of standard cells, those the locations for them are not decided during the chip planning stage, right? So those are decided during the next step, which is known as the placement stage, right? So in the chip planning stage, another important thing is that we carry out what is known as power planning. Power planning means that we create grid of power cells, that is lines of power of wires through which power will or VDD or ground line will go to each cell in our design, right? So that designing is or power planning is done during the chip planning stage, right? Then the next step is the placement. So in the placement stage, what do we do is that we decide the location of standard cells in the design, right? So we, as we mentioned, that the standard cells, the number of standard cells in a typical design is millions, right? And therefore we cannot manually do. So we the placement of the standard cells in our design is decided by a placement tool. So the physical design tool or the placement tool will decide the location of these cells based on some QR metrics, right? Or objectives. So what are the objectives during placement? So the objectives are to reduce the wire length, right? We want to reduce wire length in making connections. So why do you want to reduce the wire length? So the wire length we want to reduce. The one of the major reasons is that the longer wires have longer higher capacitance and will show more delay, right, for a signal to propagate from one end to the other, right? And therefore we want to minimize the wire length so that the delay of the signals is reduced. And therefore we want to place cells which are connected in close vicinity. We place them close together. So cells which are connected together, they are placed together. That is what the objective of placement is, right? So during placement, the tool will also try to meet the time. So it will try to reduce the delay of the critical path, right? So note that typically we design synchronous circuit, right? In a synchronous circuit, the frequency of a synchronous circuit is decided by the critical path, meaning the one which is the slowest path, right? So we need not improve the timing of all the paths in our design. We need to improve the timing of the critical path on which the clock frequency depends in a synchronous design, right? So therefore the tool will focus on the critical path, or meaning the path which is the slowest, and try to improve the timing of that particular path. Okay, and it will also try to improve or the congestion, meaning that it will try to place entities so that there are not regions in our design where many wires are crossing, right? So if many wires cross in a small region in a layout, that is what is known as congestion. The tool will try to avoid that situation, right? So these will be the objectives that will be considered by the tool or the physical design tool during placement. After placement, the next task is clock tree synthesis, right? So in clock tree synthesis, what is done is that the topology of the clock network is decided, meaning that how the clock will go from the clock source to each flip-flop in our design, right? So we try to make the topology such that the the skew is reduced, meaning that the time at which, so suppose this is the clock source, this is the clock source, and these are the end of the flip-flops. We here you have the clock pin of the flip-flops, right? Suppose this is the situation. Then the tool will try to put these buffers and wires in organized in such a way that the clock signal reaches at the same time to act all the flip-flops and in our design. That is what the ideal situation is. The tool will try to achieve it. Of course, it cannot achieve the ideal situation, meaning that the delay of all the paths are equalized, that may not be possible, but the tool will try to get as close to the ideal situation, right? This is minimization. So the tool will try to the clock tree synthesis, or the in short we call it as CTS. So the CTS tool will try to minimize the skew in our design. For wiring of the clock network, and since till during after placement we are doing the clock tree synthesis, so till now the other signals in our designs are not routed, right? So all the routing resources are available, right? So the CTS step will be done first, or the clock tree synthesis will be done first when all the routing resources are available. Why do we do this? We have a separate CTS step or clock tree synthesis step than the other routing, because the clock is a very critical element in our synchronous design, right? Because clock is basically orchestrating all the things in our design, meaning that it is like a director of a musical symphony, right? So it is basically saying that at this time do this, at this time do this, and so on. So in that sense, the clock signal is the most critical signal in a synchronous design, and therefore the highest priority is given to the clock signal in routing, and therefore we do clock tree synthesis before other routing, right? So during the clock tree synthesis, the objective is to minimize the skew, as we have discussed, and we also try to minimize the power dissipation. Why do we want to minimize the power dissipation? Because the clock signal is a signal which consumes the maximum dynamic power. Why does a clock signal consume a maximum dynamic power? The reason is that the clock signal toggles every clock cycle, right? So the activity of the clock signal is very high, right? It is always active, right? And therefore it is always consuming power in the clock network. And therefore we want to minimize this power in the clock network, and that is what one of the objectives of clock tree synthesis, right? The next task is what is known as routing. So what is done in routing? We create the layouts of the wires, right? So during placement we have placed all the cells, right? And the layout inside the cells was already made during designing of the logic gates, right? So all the transistors are now sitting on our design, but those transistors needs to be connected, and that connection or the layout of the wires are made during the routing stage, right? So the note that during clock tree synthesis we created the layout of the clock network, right? And during the chip planning stage we created the routing of the power network, right? So those things are done. During the routing stage we are basically routing the data signals, right? So in a synchronous design, typical synchronous design, most of many signals are the data signals, right? So majority of the layout of the wires will be created during the routing stage, right? So during this, what is the objective of routing? The objective of routing is to minimize the wire length and the routing areas and minimize the number of vias, right? So we discussed that vias are the elements which connects wires of two different layers, right? But these vias can have problem of reliability, right? It can also have problem of yield because vias are very structurally very small size, right? And therefore during fabrication or even during use there can be via failures, right? And therefore we would want that the number of vias in our design is minimized. Also the vias take more time or have more delay, therefore we want to reduce the number of vias in our design. So these are the objectives during the routing, right? Now the routing is a very complicated process. Why it is a very complicated process? Because there are so many nets in our design in millions which needs to be routed, right? And the deciding the layout of each of the wires is a difficult task, right? For industrial design it is not common, not uncommon, or it is very common that the routing can take a few days to complete, right? A couple of days to complete, right? So it is such a complicated process, right? For industrial design, the routing can take a few days to complete. So you run a tool, you start today, you get the result say tomorrow or day after tomorrow, and so on, right? So the routing is a very complicated step. So since it is a complicated step, it is broken down into two parts. The first part is known as global routing, and the second part is detailed routing. So we do it into two steps. First is global routing, and the second is detailed routing. So what is done in global routing? So global routing is the planning phase of routing. right? So the actual routes are not yet created, right? So the actual layout is of the wires is not created during global routing. It will be created during detailed routing. But during global routing, a plan for the routing is made, right? For example, if we want to say, consider that we want to find a path between Delhi to Calcutta, right? So in the first step we are just planning that how we want to go, maybe from here, from going from Delhi to Calcutta, we may first go from Delhi to Lucknow, from Lucknow to Patna, and say from Patna to uh, Calcutta, right? Maybe this is a route. So this plan was created during the global routing phase. Then in the next step, we will say that from Delhi to Lucknow, I will take this particular road and this particular path to reach from Delhi to Lucknow. And from Lucknow to Patna, I'll take this road and so on. That is what is detailed routing. In detailed routing, we are actually creating the layout or the path, but in the global routing, we are at the top level. We are deciding the plan for the routing, right? So why do we do it in two step? And so the one of the reasons is that the detailed routing is very complicated. As I say that it can take say 2 days to complete, for example. Now, if in an industrial design we run a tool and after 2 days it says that sorry, I couldn't find a route, right? A valid route. So that will be a very unfortunate situation because your 2 days were wasted, right? So rather than going to detailed routing, we first go to the global routing stage, which can complete in say few minutes or few hours. And if there are some problems in our design, it will be flagged during global routing phase, right? And we can fix those problems during global routing phase and then move to detailed routing. So the number of iteration to find to find a valid routes will decrease, and the design time or time to market will be less. Right. So that is what will why we break it into two phase of global routing and detailed routing. So in global routing, the tool will create a partition the layout into rectangular regions, which are known as global tiles or global bins, right? So it will say that this is my layout. I partition it into multiple grids, right? Like this. And if I want to make a wire from this point to this point, I will take this path, this path, this path, that path, and so on. So at a course level, the tool will find a path for each net, right? So the entire routing region is partitioned into rectangular tiles or global bins, and the global routing assigns a set of global bins that will be used for making connections for a given net. So this will be the set of say the global bins which will be used for routing in this particular example that I showed. Right. So the at a course level, the plan of routing is made during global routing, and in the next step, in the detailed routing, given each plan of the routing of the nets, the actual layout of the wires is decided. Right. So the detailed router decides the actual physical interconnection of nets by allocating wires on each metal layer and vias for switching between metal layers, right? So again here the tool will consider various rules that are coming from the foundry, meaning that what would be the should be the minimum spacing between the wires, what would be the minimum width of the wires, and what should be various other design rules that must be followed. It will also consider the timing of our circuit. It will also consider signal integrity, power integrity, and many other things the tool needs to consider during the detailed routing phase. Right. So once we have done detailed routing, then if some minor changes are required, then those changes are done using ECO. So ECO is what is known as engineering change order, right? So when we are at the end of the design flow, so at the end, we do not want to disrupt the things which we have already built, right? So if we need to make any last moment change, it goes through a various hierarchy of the processes, right? See, a lot of approvals will be needed from high level of designer, manager, and so on. And only then the design change will be made in a design. And that is basically known as engineering change order, right? We want to make last minute change if needed, very careful, right? We make final fixes in our design and then verify it, right? That is known as engineering change order. So there are tools which allow us to do these changes in a controlled manner and also verify whether those changes have not made any unwanted modifications of our design and our various functionalities, and the constraints are met even after engine change order, right? Once the ECO has also been done, all the verification, all the layout has been made, then what we do is that we dump the layout of each layer in a GDS file, and we write the GDS, and that GDS will basically go to the foundry for fabrication, and that closes our design flow, right? So this design goes to the foundry for fabrication. Right. Now, a few more important things that must be noted here is that design is one part, design implementation is one part. The other very important part is verification, right? So the verification we perform, we need to perform to ensure that the design works as per given functionality, right? So functionality should be there, and various other constraints must be met. So we need to verify those things, right? So the implementation tool will implement it, but the verification tool must also be invoked, and verification must also be done on our design, right? So we need to carry out verification tasks multiple times in the design flow. Why? Because if there is any problem, if the verification tool says that there is some problem in our design, we should fix right at that point. We shouldn't move ahead in the design flow if there are any problems. So to do this, at each step, after each major step that we carry out in VLSI design flow, we also carry out verification. Also carry out verification and so on, right? So the verification task is carried out whenever there is a change, that we make any major change in our design. If verification fails, then remedial actions needs to be taken immediately, right? Now, there are various methods of verification, and I'm not going to detail because I already think I'm close to running that allotted 1.5 hours. So I'll just mention that what are various types of verification. The one of the important verification, or the thing that we need to verify, is whether the functionality of our chip is as per our specification. Meaning that if you were trying to make a processor, whether the processor is able to execute the given instruction and produces the desired result, right? That is what the functionality is. So we verify those functionality using simulation, and also using what is known as formal verification. Formal verification is a type of verification in which we use mathematical properties and deductions to verify the properties more rigorously than simulation. Then we also carry out timing analysis to ensure that whether our synchronous circuit behaves properly as a synchronous circuit or not. So we use tools or technique which is known as static timing analysis for it, right? And then we also carry out power analysis to and understand whether we are meeting the power numbers. And we also carry out various physical design tasks, physical verification tasks, such as design rule check, electrical rule checks, layout versus schematic verification, and so on. Right. In addition to this, we also do power integrity checks, signal integrity checks, and so on before we tape out our chip for fabrication. Okay. So this brings me to the end of my presentation, and these are the references. So whatever I have discussed, you can find in this book, right? And also the content of what I discussed, you can also find it over NPTEL course, right, which I take, and this will be offered from, I think, from July end of this year also. So the more detail you can get into this NPTEL course, right? Me to the end of this presentation. And so let me conclude before I open it for further questions. So in this, what we discuss in this lecture? So in this lecture or in this talk, we gave a or we looked into a we took an overview of various or of the VLSI design flow. So right from the specification up to the layout, what are various design tasks that we need to carry out. So the first one is at the top level, we carry out system level design. At the end of the system level design, we have RTL. From the RTL, we get netlist. From netlist, we do physical design. From physical design, we get the we get the final layout. And during entire flow, we carry out multiple verification steps to ensure that everything's are fine. One important thing which is also done, been discussed in this lecture, is related to testing, right? The testing refers to check whether the fabricated circuit is working as expected or not, whether there are any defects or not before shipping to the customer. Those that is also considered during designing. Okay, so this brings to me the end of my lecture, and if there are questions, I can take that.
Yes, sir. Good afternoon, sir. So I want to know that in physical design planning, the area optimization play a vital role. How we can overcome it?
Sorry, I couldn't get your question. Can you please repeat?
Yes, sir. So in physical design optimization, so in floor planning, so area optimization play a vital role. How we can overcome it? Area
Uh,
optimization, I want to know.
you want to do area optimization during physical design?
Yes,
Sorry, I'm
sir.
not able to fully understand your question. So, um, your voice is a bit feeble.
I want to know about area optimization, floor planning.
Area optimization during floor planning.
Yes,
Okay,
sir.
okay. So, see, during floor planning, not much area optimization. So, the area uh, when we do floor planning, at that point of time, we know that what would be the aspect ratio of our chip and so on, right? So, just can you see my slides?
Yes, sir. Yes, sir.
You can see my slides. Just hold on. I think. Uh, can you see my slides now?
Yes, sir. Yes, sir.
Okay. So in planning stage, we have already got the boundary. So whatever I am drawing, can you see your screen?
Yes, sir.
Okay. So the area of this bounding box is pre-decided, and this comes from the packaging and other things, right? Where this die will fit in and what would be the maximum size we can allow for this package. So this area is already fixed, right? This aspect ratio is already fixed, right? Now, if we assume that this is fixed, in case it is not fixed, then we will want to pack entity as close as possible, right? If it is not fixed. If it is fixed, then the area of this bounding box is fixed. Then we need to place the entities on our or macros on our design such that constraint of area constraint is met, right? So the goal is that the we want to fit the various blocks as pack as compactly as possible during chip planning or flow. That is what we typically want to do. But the other constraints like congestion and timing and other things governs that how you want to place those blocks on the chip, right? So during the uh, chip planning stage, not much concern about area optimization is done other than compactly fitting the blocks to the layout. Okay?
Yes, sir. Thank you, sir.
Yeah.
Sir,
Yes. Please go on.
sir, please once understand the macros in logic synthesis, sir. So what type of to know in logic synthesis? Importance of cells and macros in logic synthesis.
Okay, you want to know the difference between cell and macros, right?
No, sir. Importance of cells and macros in logic synthesis. But you explained that I want to once again, sir.